Thanks, Will. Awesome. So yeah, we're here in Portland for the Buzz Workshop. So this is our hometown. So a lot of us Intel people are actually from Portland. So this is really exciting for us. This is a talk that myself, another one of our developer relations engineers, and Eugene Horton, who's the lead producer of Bohemia, did at GDC. So it was an hour-long talk. So this is kind of a 30-minute version. I'll be going through a lot of the GPA parts of it since that's what I am used to. But I'll do my best to kind of cover Eugene's and Antoine's parts, and we'll go into that as much as possible. So let's get started. Okay, so today what we're going to do is just basically go through DayZ. Just what is DayZ? I'm sure if you're a gamer, you know what it is. It's my favorite type of genre, which is the survival genre. So we'll talk a little bit about DayZ. And then we'll go over Intel Graphics Performance Analyzers, which is an awesome optimization tool. We'll do a quick little live demo. I like doing demos instead of just showing you foils and talking about, hey, here are some of the things that we can do within the tool, so it's actually a demo. And then we're going to go over optimization methodologies that we used to talk about DayZ. All right. So DayZ, basically it came onto Steam as an early access game. It was one of the front pioneers into early access, released all the way back in 2013. It's had 3 years of development on it, and it's really been one of those #1 titles, right? If we remember back to when survival genre was first getting going, DayZ was kind of a pioneer in its day. Everyone bought it when it was the Arma 2 mod, and then it came out with the standalone, and it's been a really cool game. What's awesome with Bohemia, though, is that they didn't just, as we're used to today, ship an early access title, collect the money, and then run away. They've been actually doing continuous development on it, looking at their engine, investing in their technology, and really bringing out an awesome piece of, an awesome game. Yeah, it's been on the top 25 best-selling PC games, or it is in the top 25 best PC games of all time. It's been consistently in the top 10 over the past 3 years, so it's a really awesome game, and we've had a really great time working with Bohemia. So this is what the game initially looked like, right? If we remember back in the DirectX 9 days, this is what it looks like, and basically this is where we're going. Right, so if we remember, it's been a slow transition to get from the previous slide to this slide, so I'll just kind of flash it one more time. But it's truly a lot better these days, and it's taken a lot of technical advancements and optimization to get there. So, just talking a little bit about the technical pieces behind DayZ. Basically, the DayZ features have been coming out with the engine, right? So as they make advancements into the engine, the gameplay and development is going in parallel. So at every stage, they're doing optimization. So this is a little bit different than typically games these days, or basically holiday release titles, to where you make your game, you optimize, you release, right? With this type of development model and release cycle, you're having to optimize every stage of the way. So DayZ has been, and Bohemia have been really great about basically optimizing their engine at every really large step in the rendering technology. So yeah, again, it's a test bed for future Bohemia technology. I don't know how much I can talk about this, but they're coming out with other games, and basically DayZ has been their test bed. So that's one of the reasons why they've been investing into the rendering engine for future Bohemia titles. DayZ is always kind of these large sandbox titles, so that's you have to take that into account, right? Optimization isn't just about, okay, let me figure out how to do this technique better. It's actually about taking your gameplay and then doing optimizations that don't sacrifice the gameplay, but also keep your performance at a reasonable level. A good example for this is things like bushes, right? Often when you have alpha blending, it's something that can cause some large performance variations, but it also affects gameplay. So if when doing optimizations, you have to always keep in mind how your players are going to play the game. That way you don't sacrifice gameplay just to get a couple extra frames. Yeah, one other thing that they've been looking for is console ready, and the work is never done. So we are continuously working with them to optimize DayZ and optimize other future Bohemia technologies, and we'll see some of those things that they've done later in this presentation. Okay, now talking about Intel Graphics Performance Analyzers. This is my baby here. Essentially, I'm just going to go over the basics of what this thing is, how we can use it, and then we'll dive in. So Intel GPA, it's a suite of optimization tools, right? So it's not just one, it's a suite. It's designed for optimizing games. We optimize PC games, virtual reality, mobile, pretty much any type of games under the sun. If it has an Intel chip in it, you can optimize with Intel GPA. So when would you use Intel GPA? We're all gamers here. We're all game developers. Obviously, you're going to use it when your frame rate is not so great. So let's just say we have our game, our main core render loop is done, or our main just core gameplay loop is done, right? We have our initial functionality. At that point, it's always a good idea. Let's attach a profiler. Let's see how this thing is performing. Let's take my min spec. You know, typically you develop on a nice piece of hardware. Usually that's not your min spec that you're targeting, but it's always good to take your min spec, do a profiling session on it just to see where you're at. So at that point, typically you figure out, oh, I'm running at 10 frames per second. That you know, 2 million polygon tree I put in maybe wasn't the best idea. So at that point, you can use Intel GPA, figure out actually how expensive that 2 million polygon tree is, and then go and figure out what to do from there with Intel GPA. So what do we support? I know this is kind of a giant eye chart, but we'll just quickly go over some of the highlights here. The point is that we support a lot of things, right? We have a large support matrix, which means that we try to make this tool as accessible as possible. That way, if you are using a game that is cross-platform, we are there to be able to support you in any type of spec that you want to be able to support. So on the left-hand side, we have Windows Gaming, right? So we support pretty much all your Windows host platforms. And I guess one thing to mention here first is let's talk about how GPA works so we can understand the specs a little bit better. GPA works in what's called a host and a target architecture, right? So typically your host system is where the analyzer runs, and your target system is where your game's running. So there's always that methodology and optimization that the more you affect the system that you are trying to analyze, the more incorrect your measurements are going to be. So that's why we try to separate out where the analyzers are running and the actual target of the game. That way we can take measurements with the smallest amount of performance impact as possible. So you can also run same host, same target, but typically when we talk about things, we're going to talk about a host OS and a target OS, right? So from host OS standpoint, basically choose your host OS. We can support Linux, Mac, Windows, pretty much anything under the sun. For target APIs, so we're very API-centric. So we support pretty much from the DirectX side, DirectX 9 through 12. From a hardware standpoint, we obviously support Intel. We also do support NVIDIA and AMD GPUs as well. So you might ask why we do that. Basically, we just want to be able to support the widest range of metrics as possible. Though one difference is that on NVIDIA and AMD, you won't get as deep a hardware metrics. Since we're capturing at an API level, we can show you some things on AMD and NVIDIA, but we can't show you the whole gamut of hardware metrics because we don't have access to their driver. So yeah, but we'll talk a little bit more about that in the future. We also support HTC Vive, Oculus, and new support for the Windows mixed reality stuff, if you guys have taken a look at that. So we do support UWP applications as well. So on the Android side, if you're a mobile guy, we do support OpenGL ES, basically targeting Android 4 through 6, so that's Marshmallow. On the macOS gaming side, so we support OpenGL on pretty much Sierra. So we're working on High Sierra support right now as well. Okay, so now that we're through that eye chart, let's talk a little bit about what's inside Intel GPA. So essentially, you can think of Intel GPA as 3 analyzers, right? And 1 graphics monitor. So graphics monitor is kind of the backbone of GPA. It's a process that sits there and runs in your task tray, and basically it's your launch point, right? So you launch all the applications from that. It's how you inject into an application, and we'll talk a little bit more about what injection means here in a second. But it's kind of the first thing that you do, right? You launch monitor, and then you go to profiling from there. If we look at the top right here, we have an application called System Analyzer, or the HUD. What System Analyzer is it's basically like you've used Windows Performance Monitor, right? Where you basically hit Control, Delete, pull up the task manager, go to the preferences, you see all the nice spark graphs. It's just like that, just on steroids. It has GPU metrics, memory, pretty much everything on there that you'd need to be able to figure out initially if your game was CPU or GPU bound. What's also cool about System Analyzer is that it has essentially these overrides for the render. So you can actually go and you can turn off all the draw calls, or you can just render everything wireframe. And we'll talk about why that's cool here in a second. Now down on the left-hand side, these are basically the last two are our offline analyzers. The offline analyzers, such as Trace Analyzer and Frame Analyzer, essentially you capture during the runtime of your app and then you view them in these analyzers. So graphics trace analyzer, if you use things like GPU view or VTune, it's very similar to that, but it's more GPU focused such that we can see GPU, CPU contention, we can see actually your pipeline, see the driver submitting things to the GPU and see your GPU queue. So we won't go into that as much today, but it's very helpful if you actually figure out that you are like driver bound or CPU bound. But now on the bottom left, which is kind of the bread and butter of GPA, is graphics frame analyzer. Right, if you're familiar with rendering, basically every frame is just a loop of your render. With the newer APIs, that's not necessarily true, but naively we can kind of think about it like that. What Frame Analyzer does is it captures a single frame, stores all the resources, and then allows us to play that frame back and then collect meaningful performance data and show you every aspect of that. So if you've used a frame debugger before, it's similar, but with a lot of different performance metrics, and it has kind of our performance metrics methodology built into it. So we'll talk a little bit more about that as well. Okay, so let's talk about the workflow. So there's a bunch of tools I just gave you, and you're like, wow, that's a lot. How do I even use them together? So I'll tell you. Essentially what we have here is on the left-hand side, we have our game. We connect it to System Analyzer and run it through live metrics analysis. So the whole point of what we're trying to do right now, and typically when you take a game, you're trying to figure out what piece of hardware am I bottlenecked on, right? Because if you're not optimizing for where you're bottlenecked, you're not going to get any frames back, right? So the question we're trying to ask ourselves is, are we GPU or are we CPU limited? To figure this out, we have some special pieces in System Analyzer that can help. Kind of one of the overrides that I mentioned earlier, which was disable draw calls, is actually pretty helpful. And now you might be thinking, why would I want to disable all the draw calls? Essentially what that does is it simulates an infinitely fast GPU. So if we disable all the draw calls, basically when the calls get sent from the driver to the GPU, it just discards, sends back to the CPU and says, okay, we rendered it. So you can then look at your frame rate, and if your frame rate shoots up, it means your CPU can process that many frames per second, and the GPU is probably your bottleneck. So at that point, you can say, okay, I've identified that I'm GPU bound. Now I'm going to take a frame capture. Take a frame capture, knowing that you're GPU bound, and bring it into the GPU bound tool, essentially. And we'd open that frame and Frame Analyzer. If you're CPU bound, on the other hand, we would take a trace and open that up in Trace Analyzer. So essentially, we go from this like in-game online analysis phase to an offline kind of deeper dive phase, right? Once we've figured out where we're bound. So that's kind of the initial workflow through the tools, and I'll show you a little bit of that today. Okay, so one thing that's different if you've used like Pix or any of these other tools, it's very similar. One thing we really do specialize in, though, is hardware metrics, right? It's kind of the bread and butter. It's what we were able to gather from our driver. We have, pretty in-depth counters, but how do you use all these things, right? So I can show you a spreadsheet of counters and be like, all right, you can tell where the problem is, right? And 99% of people will go, no, I can't. So what we do is basically we give you a little chart over here that basically runs you through the pipeline in the hardware and then pinpoints the exact location where the metrics say the bottleneck is. So here we have this chart. Essentially, you can kind of think of the pipeline running from the bottom up, right, with the geometry transformation first and rasterization, going all the way through the pixel backend, pixel shaders, and then into the actual memory hierarchy where we do the present. So by working your way backwards through it, we can actually figure out where the bottleneck is. So I'll show you a demo of this here in just a second. But yeah, that's the idea, is we basically have a counter basically on each side of that block that says, okay, how often is this receiving input and how often is it outputting? If your output is a lot less than your input, typically that's where the bottleneck is. You can almost think of it like a flow of water running through the pipe, right? And so basically you're just measuring at each stage to see, okay, is the water running through just as fast or faster or slower than the previous pipe, right? That's kind of a decent way to think about it. But yeah, also this whole thing and kind of the methodology is documented in our graphics developers API guide. So there's a link to it on the slides. I think Stephanie's going to upload them, and you can click on the link. Or if you just type in graphics API developer guide into Google, it's like the first link. And it basically, in section 5, it just describes all these in gory detail. And what's nice also is once you know where the bottleneck is, you're like, how would I know? What would I do if I have a shader execution stall? It basically gives you tips to say, okay, this is what you should try to do. right? Like if it's a sampler, change your memory access patterns, things like that. So you should be able to work through this, and it has some decent tips on there for you. Okay, so this is a lot of information really quickly, but Intel GPA is really easy to get started with. Essentially, you don't need any code changes to your code, so you don't have to go in and instrument and take 2 days to do that. There's no environment changes necessary, so you don't have to install a special driver, and we're not hooked into an IDE, so we're a standalone tool. Essentially, you just can take your release binary, and that's what we recommend you do, right? Because you want to be profiling the thing closest to what the customer is actually going to be seeing. So take your release binary, and basically we inject into it with GPA, and then you're good to go. So nothing that you have to do. And we're free, so that always helps too, right? So there's no hard licensing or anything like that. You just go download. I think you put in your email, and then basically you just can download all the tools for free. It just works. You don't have to renew every year or whatever. So really straightforward. It's free. Just softwareintel.com/GPA. All right, there was my pitch. So let's go into the actual demo here real quick. So we're going to be taking a look at live analysis. Since I have about a half an hour, what we're going to do is we're actually going to go and we're going to take a look at a frame that I've already opened. So typically I take you guys through the whole live analysis process, take the frame capture and everything. But since we're on Intel, we pretty much know it's GPU bound. So I opened up Frame Analyzer here for you guys to see, and we're just going to kind of look around the UI because I think this is where most people will spend their time, and I think it's the best place we can spend our time right now. So let me just kind of give you a quick tour. This is one of it's one of our oldest tools. That's why the UI kind of looks like Windows 95. But it's getting a facelift here shortly, so bear with me. The data is still really good. So up at the top here, we have a bar chart. This bar chart basically shows you from the left-hand side to the right-hand side is a frame, right? So from present to present, basically we hook on a present, capture all the GPU resources, and then end, right? So that's what we show you. Right now I have this bar graph accessed by GPU duration and GPU duration. Essentially, the biggest, fattest bars are the thing that take up the most time on the GPU. So kind of a decent way of looking at a frame initially is saying, okay, what's taking up the most time? Maybe that's what I should target for optimization. So here I have one of the larger bars selected, so I can go around and select, and we'll talk a little bit more about that. Here is kind of an API log or kind of a tree, so if I want to actually dig in to actually see what the API calls are, I can do that. Down here is really our output resource viewer. So I can see the version of that render target, or it's the final version of that render target with the selected, I call them ergs. So each API call or event, we call an erg. Most other tools will call it draw calls. We call it ergs because an erg is anything that could take time on the GPU. So things like clear calls or copy resources or dispatches that aren't necessarily draw calls, but they do have the ability to take up a large amount of time on the GPU. They don't often. I mean, dispatches can, Compute Shader can, but typically clears and stuff are fairly cheap. So most of the time we're looking at draw calls, but if I say erg, that's what I mean. Okay, so yeah, essentially this is the output resource viewer, and over here we have a bunch of tabs that give you some very helpful information based on the selection, right? So it's all kind of selection based, so based on whatever you've selected, the other panes will change and give you more information about that. You can select ranges, render targets, kind of anything you want to select. But right now, I have the largest one selected. So let's take a look. What is this thing? What have we selected? I can go over to my geometry tab and take a look. And okay, this is a nice piece of ground here. Looks good, very highly tessellated. Maybe it's 2. It all depends. So I look at my final scene and okay, it's rendering this kind of magenta color. I think you guys can see it. It's really washed out. But basically, it's this whole magenta color right here that is the ground area. So other things that we can do, since we are a live playback tool, we can actually modify the render in the scene at this point. So I can go and I can turn off all the other ergs, and then basically it removed everything else in the scene, and I can actually see where that one particular draw call rendered. So what's interesting is like here I can see, okay, I see some pink magenta things here, but when I turn all the other calls back on, they disappeared. So I'm going to go ahead and click this pixel and let's look. oh, I can see we have some overdraw, right? So basically I can take within this render target and say I rendered to that pixel more than once. So I wasted some time, right? Because I just drew right over a pixel I already drew. So, which is kind of cool. So I can basically go and I can say, okay, what other pixel did? So this guy did. So I'll select this erg. Okay, so this is the guy that drew over it. Which is interesting, right? So that was an optimization that they did. So this is an older version of DayZ. I should have mentioned that. This is an older version of DayZ, so they fixed a lot of these problems. And some of these fixes are in here, and I'll kind of pinpoint a couple ones that we'll talk about in slides. But the overdraw was definitely something that they did fix. They basically shaped up their terrain meshes a little bit so they didn't overlap as much. They built this engine themselves, so they did have some tweaking of each of the pieces of the geometry. But one of the main issues here, and if you remember, we talked about metrics analysis. If we go to our metrics viewer tab, let's figure out where our bottleneck is. So our bottleneck is actually in the sampler. So if we look here, basically how I was talking to you about the input and outputs, right? The input available is 94%. So basically it has a lot of things just sitting there waiting, ready for it to go within the sampler. The output ready is only 19%, right? That means that our bottleneck is definitely our sampler here, right? That's a pretty large range. And so that's something that we should go and take a look at. And that's what Antoine and the guys at Bohemia did, is they fixed a lot of the pieces with how the terrain was rendered and how the sampling was done. So we'll talk a little bit more about that. A couple other things within Frame Analyzer that are helpful here, or you can select ranges of things as well. So another one of the optimizations that they did is they looked at all these small draw calls and said, okay, you know, sometimes it's fine if you have a bunch of small draws, but let's see what we can do about this. So if we go in and we actually look at the shaders, which is interesting, here we have the DXIL. We'll show the HLSL shader source code if you compile your shaders at runtime. If you don't compile your shaders at runtime, we basically will show you the DXIL, which is just the intermediate language before it goes into machine code or into the ISA. So if we scroll down here, the DXIL I think is really helpful. One of the nice pieces though is just looking at the instructions, how many instructions these were. We'll see in a slide in a second, but before, approximately each of these shaders were about 215 instructions, which even though they had low GPU duration, it adds up over time, right? If we have 400 to 500 small calls that are executing double the instructions, roughly it should take about double the time, right? So we had a large amount of savings there by just optimizing these small amount of draw calls, which was very helpful. So some other things just to kind of show you around Frame Analyzer and some of the power it has. Let's do a couple experiments here. So another thing, just to show you it's not just a read-only analyzer, I can go into my Experiments tab, and let's say we have the ground here, right? Let's render this with a simple pixel shader. So if I click on that, we'll notice this bar down here in the bottom right, and it'll just sit here and process for a second. But what it's doing is it's going to play back that entire frame and then basically re-render everything and show the ground with a simple pixel shader. What is a simple pixel shader? Basically, it's just a color pass-through. So if you're familiar with pixel shaders, typically you have some complex logic in there that makes things look really nice. Simple pixel shaders were basically just taking the color yellow and passing it through. So now that it's done, if I turn the highlighting off, now we'll just see yellow. So it basically re-rendered the entire scene as if it was in the game with a yellow pixel shader. Why is that important? If we notice that we redid our timings and that our draw calls are now very small, right? That tells us that the pixel shader is the issue, which confirms that the sampler is really the bottleneck, right? So we're not only able to just look at the metrics and believe it, but we can actually do experiments, play back the frame, and actually see how it performed on the hardware, just to confirm our suspicion through the metrics. So okay, let me roll back to the slides here for a second. I want to leave at least 5 minutes for you guys to ask some questions. And we'll just kind of roll through what they found in DayZ. So here's again, that performance hardware metrics graph that we talked a little bit about when we saw in the demo. But looking at the optimizations here, so the first thing was that terrain, right? So we looked at the terrain optimizations. We found out that it was sampler limited. One of the initial problems is there was no dynamic branching. Right, on our hardware, dynamic branching is helpful, so that was definitely something that was added. Also, back on legacy hardware, essentially computing LODs used to be slower than actually just them doing the branching. So basically, now we've computed LODs, and on the newer generations of hardware, this is faster, which is one of the optimizations that they did. Also, yeah, the implementation of this dynamic branching increased the perf from 2x by about 3 milliseconds to 1.5. This was done using the sample grad instruction. So looking at the metrics tab here, essentially we saw that on the left-hand side, we see that there's a bottleneck there. The output available is about 31% where the input is 83. When the fix happened, it was about 30% output available, 56% input. That's still a bottleneck, but it's a lot less, right? And that's kind of what we're looking at. And what we can see down here is the GTI, which is the graphics to memory interface. Essentially, this the GTI read throughput was about 12 million bytes there, to where after we were about 3 million bytes. So that's almost about a 4x improvement on just memory thrash. So even though we didn't completely remove the sampler bottleneck, it's still a lot less, right? That's sometimes when you're optimizing, that's good enough, right? You won't be able to completely remove the bottleneck from that point, but it's not just linear, right? Some bottlenecks are worse than others, and you can have a bottleneck that is pretty detrimental. So that was very helpful. The second one was those small draw calls that I showed you. So basically, we were geometry transformation limited by the LOD system. We implemented an LOD system for these optimizations, and we basically simplified the vertex shader. This was those instructions that I showed you. Basically, they were about 215 each, and that allowed us to essentially get 2x faster and have 1.5x more primitives. So here we can actually see what I showed you as well, which was just that we went down from about 230 in this example to 88 on this particular shader, reducing our duration by about 2x, which is really helpful. Okay, so in conclusion, with the right tools and looking at metrics, we can easily figure out where our bottlenecks are, right? At the end of the day, DayZ's performance was increased by 2x, but sometimes when you're increasing performance, your goal isn't just to get frame rates back, but it's to enhance the visual fidelity of the game. And that's what DayZ chose to do, right? They took that extra headroom they had, and now they made the game look better by adding more models, more vertices, higher resolution textures, things that looked better. That way they could get the visual effects that they wanted. So it's kind of two ways to do optimization. You're either optimizing to get frame rate, or you're optimizing to give yourself more headroom to have nicer, better resources. So yeah, in conclusion, we went from a game looking like that to a beautiful new game. So after that, we'll open it up for any questions. Any questions? Okay. Oh, question, Kelly.
So you were mentioning the dynamic branching on the terrain.
Mm-hmm.
What exactly is dynamic branching, and how did you optimize that?
Yeah, it's a good question. I wish Antoine was here to further explain this because he did that. So dynamic branching is basically a part in your shader where you have basically two paths to go through, right? And so essentially they would choose, and I wish I knew the exact piece he did. But essentially dynamic branching helps by saying, instead of just calculating all the way through the shader from top to bottom, you might not need every piece in that. So let's just say, it basically checks if this is a piece of the terrain, like if it's farther out, I want to only calculate these particular pieces, right? So I only want to sample from these two textures instead of these four, right? So typically, without dynamic branching, you just calculate all four of those inputs and just calculate through the entire shader. Dynamic branching would say, okay, it's further out, it did that if check, so you paid the price of actually checking, and then now you're going to do less calculations. In the past, dynamic branching has been more expensive to actually do the check rather than just filling up the pipe and calculating through. So it's kind of hardware dependent. But that is one of the optimizations they made. They said, okay, we're at a point now, since the game's lifespan was about 3 years, right? As time increased, hardware got better, these techniques became better techniques to use, and that's potentially why things got faster, right? So that's how they use dynamic branching, from what I know. You know, Antoine could explain it better, but that's what he told me. Cool. Yeah, question?
Yeah, with the graphics trace analyzer.
Yeah.
So it's capturing like a temporal sample, right? It's capturing it. Do you capture video along with it?
No, it's basically just the events. So Trace Analyzer captures like ETW events or what we call ITT events. So ETW is event tracing for Windows. So think of it like just 2 regions or 2 blocks. So we don't actually capture any resources at that point. It's just we're capturing time-based regions. So if you've used like the Android profiler, I don't know, what type of games do you develop? All sorts. So like Unity has a timeline profiler as well, but basically it's showing you those particular regions, so with a name. That's kind of the use for it. If you've used GPU view, it's very similar to that. What we do that's a little bit different is we add metrics into the mix as well. So yeah, of course. Awesome. Thanks guys, appreciate all the questions.